Yeah, somebody already said that it is what is tan 30? I forgot. Sin 30. What cos 30 is
1 by root 3.
is 1/3.
1 by root 3.
1 by 2.
Root 3.
1 by root 3, right. So actually this is 1 by root 3 factor coming in because I already calculated that, and so it is. So this would be this time this divided by that is the tan of this angle, and that's I think 30. That's why this is square root 3 by 2a. That 1 by root 3 has gone in there, and that's what it is. Okay. So what I'm saying is that in this triangle, this perpendicular over the base is the tan of this angle. This angle is 30 degrees. So this therefore is this times tan 30, and somebody says 1 over square root 3, and so divide by 1 over square root 3, you get that factor. Okay. Now similarly, a2x you can easily argue. Now this is easy because the x component of the a2 and the x component of the a1 are the same. And so therefore that's also 3a by 2, except the y component is just a negative of that vector. You can easily verify that if you ask the question what is the magnitude of the a1 vector, that's square root of its x component, so that is like 4a squared over 4 plus the y component squared, so it's like 3/4 a squared. No, let's get it again. Ah, correct. Right. But I should get a, huh? 3 by 2. No, not necessarily. Yeah, so as you can see, the magnitude of A1, somebody was saying it will be A, it is not A, it is 9 plus 3 is 12, so you divide by 3 square root 3. Okay. And you get the same thing here, of course. So these are your lattice vectors. And so how do I then get my primitive lattice vectors? So if I write the vector A1, and this is the notation that you use for a two-dimensional vector, is a by 2 times 3 square root 3, and a2 is equal to a by 2, 3 minus square root 3. I've just subsumed these 4 equations into 2 equations. So this is the x component, this is the y component, x component, y component. Clear? Okay. Now you all know from Kittel, from anything that you studied in solid state physics, that you can go to the reciprocal lattice vectors, and the condition is that when you construct the reciprocal space, that's the space that you probe by, let's say, X-ray or neutron scattering, in the K space, the reciprocal lattice will have similarly their own primitive vectors, b1, b2, b3, that we'll call it, in this case only b1 and b2, and the condition is that a1, scalar product of b1 must be equal to a2, scalar product with b2, and equal to, I'll write down, but they're all a2 cross b2, etc. is all 0, and so that factor is simply equal to 2 pi, right? Because you use periodic boundary condition, remember you use quantization, the k vector becomes then 2 pi over the size times all integer vectors, and that's how you maintain periodic boundary conditions. So this is a condition that you satisfy, and a moment's thought will immediately tell you that just as these are your A1s and B1s, the reciprocal lattice vectors. I need to go through this boring stuff maybe, but you'll see in order to prove that the Dirac electrons are the ones which are relevant for graphene, you have to go through this. I have to go through this. Because there's a lot of mystery. I mean, why is it Dirac? What is Dirac? What is spin? So people don't seem to clarify these things when they come and give research talks on these topics. So please check that with this forms of A1 and B1, this you can see the dot products will give you 2 pi, A1 dot B1, right? A1 dot B1 will be A1x times B1x plus A1y plus B1y, and this, you'll see that it is just a factor of 2 pi. Okay? So now, just as you have a real space, you can also construct what is called the first Brillouin zone in the K space, and pictorially it looks like the following. It's also a honeycomb, and I think these are standard notations, but I have to learn them at this age. So you have a x-axis going like this, a y-axis going like that, and you have what's called the gamma point. And now you construct a honeycomb around the gamma point. So you have these are called the Dirac points. We'll show you why. This K, K prime are called the Dirac points in the literature. Okay. What about B1, B2, B3? You have just not one honeycomb, you have other honeycombs. So you could now construct the other one, like for instance this one. So you have the other honeycomb. So you go from the center, like the gamma point, to the center of the next honeycomb, and that's your B1. This is the primitive lattice vector in the K space. This is your first Brillouin zone, Bz. And so B2 is a vector which will similarly connect the center of this honeycomb to the next one. So this is B2. It's very clear then from this picture, though it's not very accurately drawn here, that if you now try to write down what are the K vector components, its X component will be this much, and its Y component is actually 1/3 of this. So the K vector has the same X component as the B1 vector. So if I write K vector, I'm using this color code here. This is actually quite crucial to see why you have linear dispersion as in Dirac theory of. So the X component of K is the same as the X component of the B vector, which is 2 pi by 3a, which is what I've written here. But the Y component is just 1/3 of the Y component of B1 vector, as you can see from the diagram. And so the Y component is simply 1/√3. So you take the 1/3 of this, you divide √3 by 3, and you get 1/3. Similarly, the K prime point, as you can see, that its X component is identical to the X component of the K vector, right? And that's simply 2 pi over 3a, 1 minus, but the Y component is just a negative. Okay? So, now I'm basically done with this, what you may call the boring stuff. So let me summarize what I said. So I started out by saying that a carbon atom has 6 electrons, and these 6 electrons are distributed 2 into what are called the core electrons in the 1s state, and then 4 valence electrons. 4 valence electrons can, however, be the 2s state, where 2s meaning n equal to 2, s equal, meaning L equal to 0. L equal to 0 means the wave function is symmetric, that's indicated by a circle, spherically symmetric, or the 2 goes into 2p2. The 2p2 can be either in 2px or 2py or 2pz orbitals, L equal to 1. And each of these orbitals has a butterfly wing structure like this. And therefore, when 2 carbon atoms come together, the wave functions overlap, and you get, again, bonding and anti-bonding type of 2-level system, 2-state system, they call hybridization. So you see, the 2-state system that we have, why did we give a special lecture on this 2-state system? But if you understand the quantum mechanics of the 2-state system, you understand a lot. From that you build up, remember we built it up, the tight binding model. So here graphene is also a playing ground of a tight binding kind of a model, which is what we will now discuss. And so from this, then we said that now I want to form a lattice, a 2-dimensional periodic. There is periodicity in the xy direction, no periodicity in the z direction because you have nothing. So you have a nanomaterial, okay, and your 2-dimensional system, as you understand, the Nobel Prize in Physics was also given to exotic phenomena that happens in 2-dimensional systems. You have all kinds of things like wild metals, topological insulators, all these things come about. But there are advanced research topics but we are trying to now develop in very simple terms why a tight binding model in graphene, where what is the tight binding model? Now we have constructed this honeycomb, 2 interpenetrating triangular lattices of graphene, and as I said, that if you allow only nearest neighbor hopping, this is the simplest tight binding model that you can have. You have a site energy and a hopping. You put that in a tight binding model, and I will show it to you after a little break. You form a tight binding model, and you find, when you find the energy eigenvalue, you find that they are exactly like what you have in Dirac theory. Except in Dirac theory, the electrons or positrons, fundamental particles, they're all moving the speed of light. Okay? Here, the electrons don't move with speed of light. They move with what's called Fermi velocity, which is much smaller, 1/300 times the speed of light. But still, they are massless Dirac fermions, so the entire physics phenomena that you see in the Dirac theory are now observable today in the laboratory of condensed matter and material science. Okay, so that's why you get effective mass, effective thing, everything. But here, Vf is a constant. Fermi velocity is a constant. Moreover, the mass of the electron does not appear at all in the energy. Me does not appear in energy. Alright? Which means that the excitations consequently, excitations near the K point or for that matter near the K prime point behave like massless Dirac particles. Massless Dirac fermions. That's the take-home message of today's lecture. Moreover, the linearity in Q means parity is not preserved. Good? Q transforms odd in parity, unlike usual energy, right? Underlying the fact that Dirac fermions are not only massless but are also endowed with exotic chiral properties. Helicity becomes a point of concern. So remember, helicity that you introduce as a projection of the momentum over the sigma direction now becomes important. Graphene is thus a living laboratory for studying all the exotic phenomena that are associated with 3 plus 1 dimensional massless Dirac fermions, although now in 2 plus 1 dimensional space. 1 coming from the time and 2 of course from the space. Okay? What we have discussed is only the K sector for the 2 by 2. When you bring in the K prime, you get the other 2 by 2, and that's what completes this 4 by 4 spinor representation of the Dirac business. But essentially in the extreme relativistic limit, there is no overlap because these elements are effectively equal to 0. So when you have a 4 by 4 matrix where this 2 by 2 are 0, then you can see that you can easily handle these two sectors separately. So the K and K prime points can be actually handled separately. So it's like the electron sector and the positron sector for the original Dirac problem. There's a very nice letter by Semenoff where he emphasizes this point. Essentially, you're dealing with Schrödinger-like equation, except that your energy momentum dispersion direction now is no longer quadratic but linear in Q, and you're dealing with massless like part excitations, and therefore everything that you see in relativistic quantum mechanics, spin-orbit interaction, chiral physics, helicity, they all become important, and as you know, they're the ones who lead to topological excitations and things like that. So, stop by with this. Rohit, would you like to make any comment?
So I have just one question that
the A sublattice, I map it this side as the plus side of an effective spin. It's a two-state problem. Okay, all right. And the B sublattice, that's why it's important that I use two color codes. The B sublattice is a downspin. So I only am coupling between plus and minus. So it's the same problem as this two-state thing that we did in a double well, where this side is mapped into plus, this side is mapped into minus, and I'm only going from this to that. So that's all that we are saying. So this arrow, though I use this Fermi business, I mean, I basically am doing simply this, that when I go from here to here, this side is mapped into this side. It's a two-state problem. Okay? And this is minus side. So I only go from plus to minus.